Okay. So with a great pleasure, let me introduce our next speaker, Volodymyr Mazorchuk from Uppsala University. The title of his talk is Recent Progress on Constant Problem.
Thank you very much. Can you hear me actually?
Yes.
Great.
Yes, we see your presentation.
Yeah, thank you. So I will talk about some recent progress on Constance problem. And so first of all, of course, I would like to thank the organizers for this opportunity to present this result at this conference. So my talk will be based on two papers. So the first one is joined with Marco Mackay and Vanessa Nimitz, and the second one is joined with Shraddha Srivastava. So let us start with the setup and the description of what Constance problem actually is. Assume that G is a semi-simple and finite-dimensional complex Lie algebra, and U of G the universal enveloping algebra of G. Take any G module M and consider the space of all linear maps from M to M. This is naturally a GG bimodule, and so we can also consider it as a G module with respect to the adjoint action. And then we have the greatest GG sub-bimodule of this very big bimodule, which is usually denoted by LMM, which consists of all elements on which the adjoint action is locally finite. And now, if we know that the adjoint action of G on the universal enveloping algebra is locally finite, then we immediately see that the representation map, which realizes every element of the universal enveloping algebra as a linear operator on M, so this representation map induces an embedding of the quotient of the universal enveloping algebra by the annihilator of our module into this GG sub-bimodule LMM. So this works for any module M. And then Constance problem for module M is formulated as a question whether this natural embedding of UG module of the annihilator into the bimodule LMM is an isomorphism. So this was formulated in this way by Joseph in 1918, and I will later describe some first results on Constance problem, which are mostly due to Joseph. The general status of this problem is wide open, even for simple highest weight modules, although, of course, for several classes of modules, the answer is known, and I will present it later. So I will mostly be interested about Constance problem in the setup of simple highest weight modules, which are objects of the BGG category O. So we fix a triangular decomposition of our algebra into the negative part and minus, the Cartan subalgebra H, and the positive part and plus. And associated to this triangular decomposition, we have the BGG category O. That's a very big category, but it decomposes into blocks, and we consider the principal block O0 of this category. The simple objects in this block are indexed, of course, up to isomorphism by the elements of the Weil group W of our Lie algebra G. And we denote by LW the simple highest weight module, whose highest weight is W dot 0. So 0 is a zero weight, and dot is the dot action of the Weil group on the dual space of the Cartan. So in particular, with this indexing, LE is the trivial G module, and LW0 is the simple Verma module in the block. W0 is, as usual, the longest element in the Weil group. So here are the classical results. So first of all, in the original paper by Joseph, he proved that the answer to Constance problem is positive for all Verma modules. So these are the standard objects in the BGG category O. Also, the following observation can be found, for example, in Janssen's book. If we take a Verma module which is projective in O, then for any quotient of this Verma module, the answer to Constance problem is also positive. So sometimes, under some conditions like projectivity, the answer is inherited by quotients. However, it's not always inherited. And for simplicity, let us denote by K of W the logical value of the statement that the answer to Kostant's problem is positive for the simple highest weight module LW. And the first non-trivial result for simple highest weight modules is due to Gaber and Joseph, which proved that if we take a parabolic subgroup of our while group and let W0P be the longest element in this parabolic subgroup, then Kostant's problem has a positive answer for the simple highest weight module, which is indexed by the element W0P times W0. So we have a class of elements for which we know that the answer is positive. And all this was done in the early 80s. Later on, in the 90s, it became more clear that this problem has serious consequences, so it's important for several things. So in particular, in the late 90s, Milicic and Sergel, they developed some methods how to establish equivalence between certain categories of Lie algebra modules. And their methods were that if you want to prove that two categories are equivalent, you prove that both of them are equivalent to a certain category of Harish-Chandra bimodules. For this, a number of conditions needed to be satisfied, and one of the conditions was that Kostant's problem should have a positive answer for a certain module in your starting category. And later on, this was extended and generalized to other classes of categories of Lie algebra modules in a joint work of myself with Sasha Homenko and with Katerina Stropper. So this is one of possible motivations why it is interesting to look for the solution to Kostant's problem for certain classes of modules over Lie algebras. So here are more recent results on Kostant's problem for simple highest weight modules. So first of all, if we take a simple reflection in our if we take a parabolic subgroup of our while group and a simple reflection in this parabolic subgroup, then it turns out that the answer to Kostant's problem is positive for the simple highest weight module, which is indexed by the element of the form S times W0P times W0. So the difference with the Gaber-Joseph situation is that we add here a simple reflection. And the answer is the same. The answer to Kostant's problem is positive. Then there is a result joined with Katerina Stroppel that for the algebra SLN, so in type A, the answer to Kostant's problem is constant on Kazhdan-Lustig left cells of the group W. So I recall that Kazhdan-Lustig left cells, they classify primitive ideals for the universal enveloping algebras. So the claim here is that the answer to Kostant's problem is a property of a primitive ideal rather than of the highest weight module for that primitive ideal. Then it is also shown that in type A3, there is a simple highest weight module for which the answer to Kostant's problem is negative. And this was a little bit unexpected, but that's how the situation is. Then Johan Koström generalized the first result here by basically adding here any element in the parabolic subgroup. So the answer to Kostant's problem for LW, W0, PW0 is the same as the answer to Kostant's problem for LW considered as a simple highest weight module for the Lie algebra whose while group is the parabolic subgroup. So there is a module theoretic reformulation for positivity of the answer to Kostant's problem in terms of double centralizer property with respect to projective injective module in a certain subquotient of category O. And for small cases, there is a complete list of answers, positive and negative, in type A up to SL6. So this was obtained by several people and slightly different methods. And the last result, complete answer for SL6, in the paper joined with Han-Kyun Ko and Raphael Mudgen, which was fairly recent. Okay, so this is just an overview of known results. And what one can see that there are some classes of modules for which you know that the answer is positive. There are some classes of modules for which you know that the answer is negative. You have small rank classifications, but there were no general results where you take a natural general class of modules and you say, so here for some module, the answer is positive, for some is negative, and here is the classification. Okay, and this is what I am going to present in this talk is the first two results of this kind. But all recent progress on Kostant's problem is based on the following conjecture, which Johan Koström, who was my PhD student some time ago, so he sent to me by email a couple of years ago. After some computations, extensive computations in small ranks, he came up with the following conjecture, that in type A, just in type A, if you fix an involution D in the while group, which is the symmetric group, and it's enough to consider only involutions because the answer is constant on left cells, and each left cell contains a unique involution. So this conjecture covers completely type A. So the answer, conjecturally, the answer to the positivity of the answer to Kostant's problem can be alternatively described by the following three conditions. So the first one is that if you start from the simple module and apply different indecomposable projective functors which don't kill this module, you will get different modules, non-isomorphic modules. And then the kind of a weakening of this requirement, instead of asking that they're not isomorphic, you ask that their classes in the graded Grothendieck group of O are different, or in the usual Grothendieck group of O are different. So this was a very new insight, which motivated some development on Kostant's problem, which I will talk about shortly. And the evidence for this conjecture was extensive computation in small ranks. So in connection to this conjecture, I also want to mention another conjecture, which one could call indecomposability conjecture, which was formulated in a joint paper with Tobias Kildetoft in 2016. In type A, if you take two elements in the symmetric group such that applying the indecomposable projective functor for the first element to the simple module for the second element, you get a non-zero module, then this module must be indecomposable. So that's a conjecture. The status is open, no counterexamples are known, and it's known in many cases and in small ranks. So I will denote by Km x, y the logical value of the claim that this conjecture is true for the corresponding x and y, and Km star, y the logical conjunction of Km x, y for all x. Okay. The connection between Koström's conjecture and this indecomposability conjecture is given by the following result from the paper with Hank Jung and Raphael. So if we have an involution in Sn, then the fact that the solution to Kostant's problem is positive for LD is equivalent to the conjunction of the second assertion of Koström's conjecture with the validity of Km for all x's and for d. So this in particular tells us that Koström's conjecture, the first two claims in Koström's conjecture will be equivalent if indecomposability conjecture is true. And so this result, this is not really a Lie-theoretic result. This is a result which is based on two-representation theory or birepresentation theory. And here is a brief explanation for this. The category O0 has an action of the bicategory of projective functors. And this bicategory of projective functors can be alternatively described via Zergil bimodules or Harish-Chandra bimodules. If we look at the object LW in our category O0, this object has the annihilator in the bicategory P, which acts on O0. So let this annihilator be IW. And then from this datum, we can construct two different birepresentations of our bicategory of projective functors. The first one is that P acts on the quotient of P by this annihilator. And the other one is that P acts on the additive closure of P applied to LW. And the action map defines a natural homomorphism of birepresentations from the first one to the second one. And the two representation theoretic reformulation of Kostant's problem is that the validity, the positivity of the solution to Kostant's problem for LD is equivalent to the claim that this natural homomorphism of birepresentations is actually an equivalence of birepresentations. So that's a two representation theoretic reformulation of Kostant's problem. And now I want, in the first result, it's a solution to Kostant's problem for the so-called fully commutative elements in the symmetric group. Recall that an element in a Coxeter group is fully commutative, provided that any two reduced expressions for this element can be changed one into another by a sequence of commutativity relations. So you are not allowed to use short braid relations, only the commutativity relations. In type A, we have the classical Robinson-Schoenstatt correspondence, which associates to every element in Sn a pair of standard Young tableaus of the same shape. And an element in Sn is fully commutative if and only if the shape, which is associated to it via the Robinson-Schoenstatt correspondence, is a two-row partition, is a partition with at most two rows. To formulate the answer, I need to define certain elements. So the following involution in Sn is called special, just the name. So it's like a thickening of the usual transposition. So we take a transposition and then we kind of thicken each strand of this transposition into a number of strands. And we denote this element by sigma ij. Each such element is bi-Grassmannian, which means that it has a singleton left descent and a singleton right descent. And the area, this area on which this element acts, is usually called the support of this element. And we say that two special involutions are distant, provided that their supports do not intersect. And moreover, they are separated by at least one element. So we have a support here, and there should be at least one vertical element between, vertical line between them. So this means that two involutions are distant. And now, so this is a first main theorem, which is due to Marco, Vanessa, and myself from last year. So first of all, the full version of Kostrom's conjecture is true for fully commutative involutions. Moreover, given a fully commutative involution, the answer to Kostant's problem for this involution is positive, if and only if this involution is a product of pairwise distant special involutions. So in order to kind of describe why this is true, I will need to recall that for fully commutative elements, for the Serre subcategory of O, which is generated by fully commutative elements, there is a very nice combinatorial description due to Brandon and Stroppel. So in particular, they prove one thing is that if you take a projective functor indexed by a fully commutative element and apply it to a simple module indexed by a fully commutative element, the outcome is either zero or has simple top. In particular, it's indecomposable. And they also give an explicit combinatorial description for the graded degree of that top. So in particular, it follows that for fully commutative elements, the indecomposability conjecture is true. And so the first two claims in the first two assertions in Kostrom's conjecture are equivalent. And so this suggests the following strategy. For potentially positive cases, we try to find the elements x and x prime such that the classes of the corresponding theta x LD and theta x prime LD in the Grothendieck group are different. And for the potentially negative cases, we search for x and x prime, which are different and which produce isomorphic such that the corresponding indecomposable projective functors produce isomorphic modules when applied to LD. And all this is done in terms of the temporally Lieb algebra, because that's the algebra which describes the combinatorics of projective functors which operate on the category O. I briefly recall how it is defined. So we take the Hecke algebra of the symmetric group. It's an algebra over the Laurent polynomials with integral coefficients. This algebra has a standard basis and the Kazhdan-Lustig basis. And then we take the subspace in this algebra, the ideal, which is generated by all Kazhdan-Lustig basis elements indexed by not fully commutative elements in the wild group. We factor it out, and then the outcome is the temporally Lieb algebra. Now, this algebra has a very nice diagrammatic description in terms of temporally Lieb diagrams. So these are certain diagrams where you have n dots on the top and dots on the bottom, and they are connected in pairs such that this is a planar graph. So you can write it without intersections in the plane. In terms of these diagrams, our constant positive fully commutative involutions look as follows. So if we have cups and caps in this graph, they all must be nested or separated by a vertical line. So that's a typical example of a constant positive element. And a constant negative element means that you have two cups which are next to each other and which are not separated by a vertical line. Yes, and then to prove constant negative cases, it's relatively easy. So if we have a potentially constant negative elements, we should just produce two elements x and x prime such that applying this in decomposable projective functors to LD gives isomorphic modules. And here you have just a typical example how these x and x prime should look like, and this generalizes to the general case. The constant positive part is much more tricky and much more technically involved. Using some adjunction and using some play with adjunction, it reduces to the question of combinatorics of multiplication of elements in the Kazhdan-Lustig basis. So you need to produce some element W with the properties that theta D has different multiplicities in theta W inverse theta X and theta W inverse theta X prime. And in most cases, there is an obvious choice which works, but it doesn't work in all cases. So in a small number of cases, a much more delicate adjustment for the element W is necessary, and this requires case-by-case analysis, which is very technical, but at the end it works. And this gives the proof of the theorem. And the classification result for Constance problem, for the positivity of Constance problem for fully commutative elements, is kind of explicit enough to be able to do the enumeration. And you can compute how many fully commutative elements are constant positive, constant negative, and compare them. So it's classical that the number of fully commutative elements in the symmetric group is given by the Catalan number. And then using our main theorem, one can prove that the number of fully commutative we start that the number of fully commutative involutions in a SN is given by this binomial coefficient. And then using our main theorem, one can prove that the number of constant positive fully commutative elements is actually given by the nth Fibonacci number. Moreover, if we also make this, if we refine this question and look for constant positive fully commutative elements with a fixed A value, so A value, A is Lustig's A function, which is an interesting function which plays important role in Kazhdan-Lustig theory. Then if we fix the value of the A function, then constant positive fully commutative involutions are actually indexed by coefficients in the Fibonacci polynomial. So for Fibonacci polynomial is a polynomial which is defined using a recursion, which is similar to Fibonacci's recursion for the Fibonacci numbers. And after that, you can actually have the following consequences that asymptotically, if you send n to infinity, then the answer to Kostant's problem for fully commutative elements is almost surely negative. So asymptotically, there are no Kostant positive fully commutative elements, neither there are Kostant positive fully commutative involutions. However, if you fix the A value and send the n to infinity, then the answer to Kostant's problem for fully commutative elements of a fixed A value is almost surely positive. So if the A value is fixed, then asymptotically all elements of that A value are Kostants positive. So it looks, at least this part was to me quite surprising. So this is the first main result. It's about Kostant's problem for simple highest weight modules. Another natural class of modules for which one can look to the solution to Kostant's problem is the class of generalized Verma modules, which are, for example, parabolic Verma modules, which are standard objects in the parabolic category O. Recall that the original result of Joseph says that Kostant problem has positive solution for all Verma modules. So here in the second part of the talk, I look at solutions to Kostant's problem for parabolic Verma modules for two types of parabolic in type A. So if P is a parabolic subalgebra of G, which contains the Borel subalgebra, then we have the corresponding parabolic category O0P. That's a full subcategory of O0, which consists of all objects on which P acts locally finitely. We have the parabolic subgroup of W, which is associated to P, and we can consider the set of shortest Kosach representatives of W modulo WP acting on the left. And then our parabolic category is just the third subcategory of O0, which is generated by simples indexed by these shortest Kosach representatives. And we have the corresponding Zuckerman functor from O0 to O0P, which takes the maximal quotient of an object, the maximal quotient which belongs to the parabolic category. And the parabolic Verma modules are obtained by applying this functor to the usual Verma modules. Again, so parabolic Verma module is a quotient of the usual Verma module, and Kostant's problem doesn't behave very well, is not inherited by quotient. So it's a natural question, how about the answer to Kostant's problem for these parabolic Verma modules? And we consider two cases with Shradas-Srivastava, the case of minimal parabolic and the case of maximal parabolic. So in the case of minimal parabolic, so what is a minimal parabolic? Minimal parabolic means that we take the Borel and add one negative simple root. So simple roots are indexed by elements between 1 and n-1. And in order to describe the answer, I need some technical definitions. So GK denotes the centralizer of the transposition KK plus 1 in a Sen, and GK hat, the subgroup of GK, consisting of all elements which fix K and K plus 1. Then tau ij and k is the unique element of Sn, which sends I to k, j to k plus 1, and preserves the natural order on all the remaining elements. So x and k is the set of all these tau ij and k, and x and k plus the set of all tau I plus 1 and k. So here is the description of solutions to Kostant problem for generalized Verma modules for minimal parabolics. So now if we have the shortest Kosach representative, which indexes simple modules in our parabolic category, then the answer to Kostant's problem is positive for the corresponding parabolic Verma module, if and only if the index belongs to the set obtained from x and k plus by applying the group GK hat. And this is also equivalent to the claim that the annihilator of our parabolic Verma module is a primitive ideal. And the crucial ingredient in all this thing, this is not a very easy statement, but the crucial ingredient is that for minimal parabolics, parabolic Verma modules are cokernels of inclusions between two Verma modules. And for such cokernels, there is a very explicit description of the Sokol, which is given by another paper with Han-Kyun Ko and Raphael Mugel. So that's the main ingredient why all this was possible. So the first part was about minimal parabolic, and now the second extreme case is the maximal parabolic. So what is the maximal parabolic? We take the whole algebra and we throw out one negative simple root. And again, as usual in the parabolic subalgebra, for parabolic category O, the simples are indexed by shortest Kostant representatives of the big wild group modulo the parabolic subgroup. And these elements are, in this case, in natural bijections with words of lengths n in the alphabet up and down, where, so if you throw away the case root, where we have exactly k letters up. And in order to formulate the statement, I define y and k at the set of all words of this form, which satisfy the following conditions. If k is smaller than n minus k, then all downs appear next to each other. If k is greater than n minus k, then all ups appear next to each other. And if k is equal to n minus k, then either all downs or all ups appear next to each other. And now I can formulate the statement. So if k is one of the elements 1, n minus 1, or n divided by 2, then the only parabolic Verma modules in this maximal parabolic for which the solution to Constant's problem is positive are the Verma modules indexed by the identity or by the element W0 QK W0. And these two elements, for these, the answer to Constant's problem is always positive. So this was this lemma from Janssen's book, which I mentioned before, because that's a quotient of a projective Verma module. And that's exactly the Gaber-Joseph element. This parabolic Verma module is simple, and it's indexed by the element exactly from the statement by Gaber and Joseph. So in this case, the only positive parabolic Verma modules are those which are expected. Everything else is negative. And if k is not equal to n divided by 2, then the parabolic Verma module is constant positive, if and only if W belongs to the set y and k defined on the previous slide. In any case, if one looks at this, one sees that constant positive parabolic Verma modules, it's a very small part of all parabolic Verma modules. And this is a maximal parabolic. Here, everything is defined by combinatorics of fully commutative elements. So here, the crucial ingredient is this combinatorial and diagrammatic description of maximal parabolic category O by Brandon and Stropper. So thank you very much. And if you want to learn more about category O, please take a look at Uppsala Algebra channel on YouTube, where there are many lectures on it. Thank you.